And it's a pleasure to be joining you all virtually, but I certainly wish we were all together in person in Chile. Was really looking forward to this meeting. So I will mostly be reviewing this annual review article, and I like to joke, I don't know how we wrote 70 pages about what is still basically an elusive population of black holes living in mass between the stellar mass and the supermassive. And of course, we know Andrea Ghez and Reinhard Genzel just got the Nobel Prize for their work in the galactic center, which roughly sets the lower mass of supermassive black holes that we know. My particular interest in filling in the mass distribution between the stellar and the supermassive is that we don't think supermassive black holes formed at their current mass. And so we think there ought to be relics of the seed formation processes that we can find in the universe today. So you heard in great detail about different seeding mechanisms and challenges for each of these from Zoltan. The piece that I'd like to add, and I think many of the speakers will discuss in this session, is how relatively local and perhaps pushing into higher redshift observations of mass distributions, but also environment. So what galaxies or star clusters these black holes are found in, and whether there are correlations between the properties of the stars and the mass of the black hole. All of these demographics could provide information about which of these seeding mechanisms was dominant. Now, in the course of writing this review, I became more and more pessimistic that it would be easy to tell between early seeding mechanisms that were heavy, so these more direct collapse type models, and the population 3 stars, particularly if we're able to invoke Hyper-Eddington totally buried invisible accretion very early. However, this gravitational runaway path should be happening throughout cosmic time and should be leaving black holes in star clusters outside of galaxy nuclei. So I still view that as a potentially detectable or rule outable process, and perhaps we saw the start of one of those runaways in a recent LIGO event. All right, so how can we go about searching for these black holes below, or around and below 10 to the 5? And of course, the gold standard and what we would like to be doing is using the dynamics of gas or stars in the sphere of influence of these black holes. And when I started my thesis and started thinking about this problem, Carl Gebhardt had just published an upper limit of 1,000 solar masses in the center of M33, which had the community thinking, okay, as you get into these low mass dwarfy galaxies, you no longer find supermassive black holes. But there was this other case in a galaxy only 4 megaparsecs away, very similar in properties to M33, NGC 4395, which showed clear evidence for an accreting black hole. And so the question is, in this sort of few times 10 to the 9 mass range, at least, what fraction of galaxies host black holes? And here's basically all of the dynamical measurements in stellar systems in the literature to date. You heard a great discussion of the galaxy nuclei from Anil, so I won't go over this again, except to say that roughly speaking, half of galaxies in this below 10 to the 10 mass range show evidence for a massive black hole from dynamics. And as Anil said, it's a complete sample if you think about only the early type galaxies. Far more contentious and challenging is the question of whether there are black holes in globular clusters, so you get to even lower mass stellar systems. There is no definitive evidence to date, I would say, in any of these stellar systems. We might hear about something exciting later in the session. Even in the same system with the same data, the same author has come to different conclusions about whether or not these systems host black holes. There's just an angular resolution challenge. There's also the challenge of cluster of remnants, of dark remnants that is still model dependent. And this is in the bottom right here, a plot from Tuan Do just showing that for a massive cluster like G1, if you had the angular resolution afforded by an ELT, you might be able to convince yourself that there was a massive black hole in that system. So that's where we are with dynamics, which leaves us to then try to expand the volume we can reach with using accretion. The challenge here is that the black holes are such low mass that even one or a few stars can compete in luminosity, even if the black hole is radiating at a substantial fraction of Eddington. So supernovae, X-ray binaries, star formation, dust, all of these things make it very challenging to actually figure out your completeness. You can find awesome examples of AGN in galaxies, even down to a few times 10 to the 7 in stellar mass, but understanding the number densities and the occupation fraction is very challenging. I think the best, easiest to control situation is to use X-ray. This is work led by Brendan Miller and Elena Gallo, but there are a few works in the literature now that show if you look at local galaxies, again, in this few times 10 to the 9 stellar mass range, at least 20% of them show signs of accreting black holes. This is once you correct for X-ray binaries in the galaxy nucleus. And that's probably a lower limit. This is getting down to about 10 to the -4 Eddington. Tidal disruptions are starting to get into the game. Anil mentioned this briefly yesterday. This is work from Van Velsen, 2018, just showing that you cannot describe the luminosity function of TDEs given his understanding of their detection efficiency without positing that at least down again to this few times 10 to the 9 mass range, that roughly equal fraction of those galaxies host black holes as Milky Way mass. So constant occupation fraction down to about LMC mass. And finally, pushing down to what is perhaps our best case for a true intermediate mass black hole. This is HLX1. It's, we think, was in a small galaxy that was tidally stripped. It shows signs for state changes. It can get quite luminous, up to 10 to the 42 ergs per second in the X-ray. And the best guess is that it is powered by a 10 to the 4-ish solar mass black hole. And so here's just a scorecard where we stand. LIGO and advanced LIGO is pushing into this 100 solar mass range, and we'll push a little bit higher up. HLX1 and maybe a couple other sources like it live in this 10 to the 4 regime, and then this combination of stellar and gas dynamics plus accretion gives us a pretty good view at 10 to the 5 and above. If we quantify things in terms of the occupation fraction, so what fraction of galaxies as a function of their stellar mass we believe host massive black holes at their center, from the combination of dynamics and accretion, we think that it down to at least 10 to the 9, that occupation fraction is still pretty high. It's not 1%, it's not a fraction of a percent, sort of the low numbers that I think many of us were thinking when I started my thesis in M33 was an upper limit. Rather, it seems that most, but probably not all, galaxies in this mass range host black holes. We have almost no quantification of this fraction down in the 10 to the 8 and below stellar mass range yet. And then here's where the sort of notional TDE constraint lives, here up at a few times 10 to the 9. And then I'm just showing some of the modeling constraints. The Bellvari is direct collapse, and then the Ricarte and Nataraja and heavy and light constraints. And you see that it's going to be challenging to distinguish between these models if we can't extend our constraints to lower stellar masses. So it's also useful to consider how the black hole correlates with the galaxy that it's found in. Kaihan yesterday was talking about the importance of including upper limits. So we have fit these scaling relations, including rather constraining upper limits that Nadine has published from nuclear star clusters. When those are included, we see no evidence really of a break in skin. This is now black hole mass versus velocity dispersion, and the dispersions at the low end are of the nuclear star clusters. And again, no evidence of a break. Minor difference between blue and red galaxies in this scaling relation. And that's a question that Anil alluded to in his talk, but that's hopefully we will start to have enough information to ask whether the occupation fraction or the mass distribution is different in the early and late type dwarfs. You could imagine assembly bias. You can imagine a different path for how the black holes or nuclear star clusters got there. So that's an interesting question, I think, going forward. We also looked at this much larger scatter, but useful relationship between stellar mass and black hole mass. You can also see work by Amy and Marta in this regime using HN. And if we then take the combination of the occupation fraction, the known galaxy luminosity function, and the scaling relation, we can put new constraints on the black hole mass density below 10 to the 6. This is important, for instance, if you want to predict the extreme mass ratio in spiral rate for something like LISA. And you can see that even with our very best estimates, there's still quite a large range in possible number densities for these black holes as you get below 10 to the 6. And I just, on the right, you can see the range of occupation fractions that I assumed. Both of these are basically pulled out of a hat, but consistent at least with all known observations. The blue line is if you assume that basically every nuclear star cluster hosts a massive black hole. And of course, to date, we've only really figured out how to look for massive black holes when there is a star cluster. So one of the big embarrassments, maybe we'll talk about later in this conference, is that we still don't know whether or not the LMC hosts a massive black hole at its center. We really just don't know where to look. So I mentioned earlier in my talk that while I'm somewhat pessimistic that we'll be able to distinguish between early seeding models, POP3 versus heavy, using this demographic information, that I did think the gravitational runaway path could be constrained using the population of black holes that are found outside of galaxy nuclei. And so I wanted to spend a little bit of time talking about my vanity project that I'm working on during my sabbatical, which is a search for wandering black holes in the Milky Way. And there are a number of ways you expect that some black holes, intermediate mass black holes, may be deposited in the halo of the Milky Way. One of them is if you make black holes in star clusters, then you will have, if any of them are dense enough or massive enough, in fact, to have a gravitational runaway, you would expect black holes outside of the nucleus. But you also expect that galaxies, satellite galaxies falling into the Milky Way could be completely disrupted, leaving only the black hole and a small cluster of stars. Or finally, it's been suggested by Ryan O'Leary in his thesis that there may have been very early merger events that could have made recoils and deposited intermediate mass black holes. So I'm just going to focus on this first path because I think it has to happen, but of course we have no idea whether these satellites host black holes if they're falling in quite early. Just taking the dynamical evolution of these stellar systems from Ryan O'Leary's work, what we would expect is basically 20% of the mass in the black hole to remain bound in stars. So these are clusters of stars of 500 to 5,000 stars with sizes of roughly a parsec. And this is what one would look like in decals at 30 kiloparsecs from us. So we're doing a search using the combination of Gaia and decals. This is in collaboration with Lachlan Lancaster, a graduate student at Princeton, and Yuan Senting and some others. And without going into the details, since I don't have time, here is just modern predictions for how many of these you might expect on the left as a function of black hole mass. This is a cumulative number of wandering black holes if every single disrupted satellite brought in a massive black hole. So this is extremely optimistic. And in blue is using that M sigma relation to estimate a black hole mass, and in green, the stellar mass to black hole mass. So you can see that these vast extrapolations lead to real uncertainties in this population. And the M sigma root is what previous work, Rashkoff and O'Leary were using. Here are just the number of stars on the left, the number of stars we could detect in Gaia for these different star cluster masses, and this translates into the completeness as a function of distance that I'm showing on the right. So a 500 star cluster, which is roughly, 1,000 solar mass black hole, we can detect out to 15 kiloparsecs, and a 5,000 star cluster we can detect basically anywhere. And I should mention that because these star clusters need to be, the galaxies need to be completely disrupted in the context of this semi-analytic model, SatGen at least, all of these disrupted clusters are deposited within 20 kpc. So that's basically our search radius. And the search is ongoing, but so far we haven't detected anything, so no Nature paper for us, but these arrows are roughly the upper limits given the volume we're able to search with decals. And so twiddle consistent with your expectations from this black hole galaxy relation, although of course, again, the occupation fraction for these satellites could be 0. They're falling in very early. They may not have had time to grow. So that's where we are on our search for wandering black holes in the Milky Way. As Anil mentioned yesterday, another promising way to get at this population, maybe through tidal disruption rates, especially with the Rubin coming online. And in our next talk, we'll hear about other ways of getting black holes that don't necessarily stay at the centers of their galaxies from Amy. So just in the couple minutes I have left, the future is extremely exciting for this field. Of course, a gravitational wave experiment like LISA should be detecting the mergers of intermediate mass black holes all the way out to redshift 10. We should be seeing tidal disruption events from off nuclear black holes, hopefully, if we figure out how to identify them, as well as extreme mass ratio in spirals, potentially from the same white dwarf intermediate mass black hole pairs. So that's a super exciting prospect. With the advent of extremely large telescopes, we should be able to find or rule out 1,000 solar mass black holes in stellar systems within the Milky Way, as well as get to 10 to the 4 solar mass black holes within at least 5 megaparsecs. And so this will totally change the demographics from dynamics game once we have the spatial resolution and depth afforded by extremely large telescopes. And so I guess I'm done, and I look forward to seeing all of your questions on the Slido and chatting later this afternoon.